Hello everyone, so I'm Michaël Aupetit. I will share this session, Star 3, on scalar field topology and astrophysics. We will have two interesting talks today, and so let's start with the first one. So it's about scalar field comparison with topological descriptors, properties and applications for scientific visualization. And the talk will be given by Lin Yan.
Hello everyone, I am Lin Yan, a PhD student from the University of Utah. I am presenting our paper titled Scalar Field Comparison with Topological Descriptors, Properties and Applications for Scientific Visualization. This is a collaboration with Talha bin Masood, Raghavendra Sridharamurthy, Farhan Rasheed, Vijay Natarajan, Ingrid Hotz, and my advisor Wang. Given a set of scalar fields, topological descriptors such as merge trees play an essential role in capturing the shape of scalar field data. They provide fundamental tools for scientific visualization in terms of abstraction and summarization. For data comparison, feature tracking, and ensemble analysis, a large number of comparative measures have been proposed targeting different topological descriptors. For example, given two merge trees T1 and T2, a comparative measure such as the tree edit distance can be defined between the two merge trees. Such comparative measures are used in a number of visualization applications, such as symmetry detection, shape matching, outlier detection, and clustering. An overview of a visualization pipeline can be summarized as follows. Given a set of scalar fields, we compute a type of topological descriptor such as the merge tree for each scalar field. We then apply a chosen comparative measure for these topological descriptors. Finally, we utilize the results in various visualization tasks. Our STAR paper aims to categorize, summarize, and analyze existing approaches that utilize comparative measures and identify open problems and opportunities for future work. Our work is especially motivated by the following questions. First, which role do topological methods in comparative analysis and visualization play? And what are the typical applications? Second, how are comparative measures used in visualization tasks? We are also interested in both the mathematical foundations and properties of comparative measures and their use in real-world visualization applications. Now I highlight our contributions. We provide a classification of comparative measures for topological descriptors. We collect a set of desirable properties of a comparative measure. We survey how comparative measures are used in visualization tasks. We derive a list of opportunities and challenges for future work. We review representative papers in the field of computational topology, topological data analysis, and visualization that develop or utilize topological descriptors for the comparative analysis and visualization of scalar fields. Our primary categories are based on visualization tasks. Specifically, we classify papers based on the complexity of scalar field data. We identified three categories of data where topological comparison have been applied: single fields, time-varying fields, and ensembles. A single field is a scalar valued function defined on a 2D, 3D, or higher dimensional domain. Comparative measures help extract, visualize, and highlight similar structures within a single field, which are commonly referred to as the symmetry detection problem. These comparative measures also enable the comparison of two or more single fields for shape matching and retrieval. A time-varying field is a dynamically changing field, and is defined over the Cartesian product of a spatial domain and a time axis. Comparative measures between successive time steps have been used to detect periodicity, key events, or outliers. They also drive feature tracking in time-varying data. An ensemble refers to a collection of scalar fields that are indexed by a collection of parameters. For ensembles, comparative measures help identify similar or dissimilar behavior between members. They help identify clusters of members, outliers, or unique members of the ensemble. More recently, Comparative measures have been used to compute statistics that describe the distribution of the ensemble members. We begin by review the technical foundations for scalar field topology. Popular topological descriptors for scalar field data can be classified into three categories. Set-based descriptors such as persistence diagrams and barcodes. Graph-based descriptors such as merge trees, contour trees, and Reeb graphs. And complex-based descriptors such as Morse and Morse-Smale complexes. We give a few examples of topological descriptors considered in our survey. We begin by introducing the persistence diagram and its variants. Given a single scalar field, the persistence diagram tracks the topological changes of its sublevel set. We will give a simple example of a persistence diagram. The graph of a one-dimensional function is shown on the right. Its zero-dimensional persistence diagram is shown on the left. The persistence diagram captures how connected components in the sublevel sets of the function change as we increase the threshold A. At A0, a single component appears in the sublevel set, which contains the global minimum P0. As we increase the threshold A. At A1, a second component appears containing the local minimum P3. As A increases to A2, a third component appears in the sublevel set containing local minimum P1. At A4, the component containing P2 merges with a component containing P1. That is, the component containing P2 disappears, while the component containing P1 remains. The appearance and disappearance of the component containing P2 gives rise to a purple point in the persistence diagram. Similarly, at A5, the component containing P1 merges with a component containing P3 and disappears. At A6, the component containing P0 merges with the component containing P3 and disappears. Persistent homology captures the appearances and disappearances of components. Such a summary is either represented as a set of intervals, called the barcode, or as a set of points in the plane, called the persistence diagram. The persistence landscape is a function-based representation of a persistence diagram. It maps a persistence diagram into a function space. On the high level, it is constructed by rotating the points from the persistence diagram by 45 degrees, and build a number of piecewise linear functions. The mathematical definition of a persistence landscape is given as follows. Without going into the mathematical details, a persistence landscape allows the information contained in a persistence diagram to be easily integrated with tools from statistics and machine learning. Now, we would like to discuss graph-based topological descriptors, such as a Reeb graph and its variant. What is a Reeb graph? Given a height function f defined on a double torus, we consider the topological changes in the level sets of f. Given a threshold t, the level set of f at t is the collection of points whose function value is equal to t. As shown here, there are three connected components in the level set at t. As t increases, a Reeb graph captures the appearances, disappearances, splitting, and merging among the connected components in the level sets. In other words, a Reeb graph generates a topological skeleton of a scalar field. On the other hand, a related but slightly different topological descriptor, called the merge tree, captures the topological changes in the sublevels sets of a function f. Consider a function f defined on the same double torus. We study sublevel sets of f at the threshold t. That is, all points whose function value is smaller or equal to t. As t increases, the merge tree captures the appearances and merging behavior among the connected components in the sublevel sets. Finally, we study complex-based descriptors such as Morse and Morse-Smale complexes. They are based on the gradient behavior of points in the domain. Given a 2D function visualized in 3D, at a regular point x, an integral line is a maximal path whose tangent vectors agree with the gradient of x. A Morse complex of F is the set of all descending manifolds, which include a critical point and all regular points whose integral lines end at the critical point. In the example on the left, a descending manifold corresponds to the red bump. The ascending manifold of a critical point is the point itself together with all regular points whose integral lines originate at the critical point. In the example on the right, an ascending manifold corresponds to the light green valley. Intersecting both descending and ascending manifolds, we obtain a Morse-Smale complex. Now, having reviewed a number of topological descriptors, we need to discuss comparative measures. There is a number of ways to compare persistence diagrams. We review two classic distances between persistence diagrams, namely, bottleneck distance and Wasserstein distance. Given two persistence diagrams D1, D2, we compute their bottleneck distance by finding a bijection between the points of the two diagrams. The bottleneck distance finds the minimal L-infinity distance among the matched points across all possible bijections. On the other hand, the degree p Wasserstein distance takes the sum of p powers of the L-infinity distances between corresponding points, again, minimizing over all bijections. Now, there are a number of comparative measures developed for graph-based topological descriptors. We give a few examples for comparing merge trees. Tree edit distance considers edit operations between two trees, which include delete, insert, and relabel operators for the node on merge trees. A cost function is imposed for each edit operation. The tree edit distance is the minimum cost of node operations that transform one merge tree to another. Another distance for labeled merge trees is defined as follows. Given a set of merge trees, we can convert each tree into a matrix representation called an ultramatrix. In an ultramatrix, the values on diagonal are the function values of corresponding leaves, and the values off diagonal are the function values of lowest common ancestors between two leaves. The interleaving distance between the merge trees is the L-infinity distance between these matrices. Finally, let us compare Morse complexes and their variants. There are only a few comparative measures have been developed for complex space topological descriptors. These descriptors are more sensitive to perturbations in the scalar fields, making it difficult to design effective comparative measures. We give an example for an extremum graph on the left. It is a sparse subset of a Morse-Smale complex. It connects critical points along steepest ascending or descending lines, which join adjacent extrema. The right shows a possible match between two graphs, which will be used in extreme graphs comparison. We give a very high-level introduction of distances between extremum graphs. In order to compute distance between extremum graphs, we need to find a row-valid mapping that minimizes the maximal distortion between the vertex set and edge sets. Distance between extremum graphs is defined as the value of minimized maximal distortion. For our report, we surveyed about 200 papers from a number of visualization, computational topology, and topological data analysis venues whose title and/or abstract contain keywords relevant to topological descriptors and their comparative measures, such as persistent homology, merge trees, scalar field comparison, etc. We complement our survey with a visual literature browser developed with the service framework for an interactive navigation of the report. The comparative measures have enabled a wide variety of visualization tasks. To showcase their applications in visualization, we introduce a number of notions. SF stands for scalar field. It labels the primary categories, single field, time-varying field, and ensemble. TD means topological descriptor. This represents the type of visualization tasks. And CM stands for the comparative measure used for comparing topological descriptors. We begin with visualization applications for single fields using various comparative measures. The comparison of single fields has many applications in scientific visualization, and in many cases serves as a building block in comparing time-varying scalar fields and ensembles. It plays an important role in tasks such as symmetry detection and shape matching. The former finds applications in the visual analysis of biomolecules, and the latter is essential for comparative visualization and computer vision. For symmetry detection, Thomas and Natarajan used contour trees as their topological descriptors. They defined a distance between subtrees of contour trees to measure similarity between subregions. The demonstrated applications in molecular biology, where detecting repeating substructures in biomolecules is crucial to understand their shape and function. In this figure, we see various symmetries identified within the buckyball and vortex simulation datasets. These two figures are full volume renderings. The left is for vortex simulation dataset, and the right is for buckyball dataset. They provide a number of symmetric regions in each dataset. Their method can also be used in applications such as symmetry-aware transfer function design and isosurface extraction. A second example for single-field visualization is related to shape matching and retrieval. Feng et al. Studied the problem of computing feature correspondences between two non-rigidly deformed surfaces. They used topological descriptors called the feature graphs, which are one-dimensional skeletons of simplified Morse-Smale complexes. Feature graphs are compared using a minimum cost graph matching algorithm. For shape matching using feature graphs, we can see point and patch correspondences between hands in different poses. Their work also showed correspondences of various parts of the head mesh data, together with the results of texture transfer. Now, we discuss visualization tasks involving time-varying data. Saikia and Wang proposed a global similarity measure for feature tracking in time-varying fields using subtrees of the merged tree. Subtree similarity is based on a combination of spatial overlap and chi-square distance between local histograms. They applied their method to track primary and secondary vortex structures in the 3D time-dependent flow behind a cylinder. As shown here, secondary vortex structure has been tracked backwards and forwards from time step 45. On the other hand, Sridharamurthy et al. Utilized the tree edit distance in applications such as detecting periodicity and computing temporal summaries. They used a distance matrix between time steps to detect key events and summarized the von Karman vortex street dataset. Rows and columns correspond to the 120 time steps in the dataset. The corner of the black box shows a big structure change around time step 28. We can also observe several clusters from this distance matrix. Finally, we give a couple of examples of using comparative measures in visualizing ensembles. Favelier et al. Described a framework called Persistence Atlas that uses a persistence map for clustering ensembles. The persistence map is a derived scalar field that captures the spatial distribution and density of extrema in the input field weighted by their importance. L2 distance is defined between two persistence maps for comparison. Top right figure is the distance matrix for the persistence maps arise from an ensemble of a synthetic scalar fields. Left bottom image shows a 2D projection of persistence maps. Their method can be used in clustering and classification of ensemble members. In a different line of work, we used interleaving distances to study a structural average of an ensemble of labeled merged trees. Such a structural average, referred to as a one-center tree, minimizes its maximum distance to any other tree in an input ensemble. Given a list of numbers, we can calculate their numerical average. Now, replacing each number by a merged tree. We can use merged trees as inputs, and compute its structural average. Having reviewed applications of comparative measures in visualization, we now survey desirable properties of comparative measures. Our secondary categorization is a set of desirable mathematical and computational properties with respect to comparative measures. This table reports desirable properties for comparative measures surveyed in this report. we discuss desirable properties of a comparative measure D between a pair of topological descriptors A1 and A2. It is desirable to require D to be a metric. That is, D satisfies these four metric properties: non-negativity, identity, symmetry, and triangle inequality. If the identity is not satisfied, D becomes a pseudometric. There are many notions of stability for a distance metric D with respect to the underlying scalar field. This can refer to the questions whether D is stable with respect to simplification or perturbation of the underlying function. We give the mathematical definition of L-infinity stable for D here. There are many variations on the notion of discriminativity. For example, using a comparative measure D0 as a baseline, D is considered to be more discriminate than D0 if for some constant C, the distance between A1 and A2 under D0 is smaller or equal to C times their distance under D. Many existing works used bottleneck distance as a baseline. Finally, we discuss computational complexity. We investigate the computational complexity of a comparative measure D in terms of the time and space complexity, as well as scalability and parallel computing. We also review a list of open-sourced implementations. We now give some examples of comparative measures and their properties. We start with the bottleneck distance. In the most general case, bottleneck distance is an extended pseudometric. It is a metric when the persistence diagrams are locally finite multisets. Bottleneck distance is proven to be stable with respect to small perturbations of the input function. And it is usually used as baseline to determine the discriminativity of a newly introduced comparative measure. Using the geometric structure of data for a bijective matching of persistence diagram, the bottleneck distance can be computed in roughly n log n time, where n is the number of points in the persistence diagram. On the other hand, p-landscape distance is proven to be a metric and is stable. But it is not discriminative. Actually, bottleneck distance is discriminative with respect to the p-landscape distance. The overall complexity of computing the distance between landscape is n square. For merge trees, the edit distance between merge trees is a metric. It is not stable because small changes in function values may cause pairing switches in the merge tree, resulting in a large increase in distance. The edit distance is more discriminative than the bottleneck distance, and it can be computed quadratic time. For labeled merge trees, the interleaving distance is a metric. It has been proven to be stable. It is conjectured that interleaving distance is more discriminative than bottleneck distance. The computation of interleaving distance takes quadratic time. Finally, the mathematical properties of distance between extremum graphs is not well studied. It is proven to be a metric. However, we do not know if it is stable or discriminative. Its computation is NP-hard. Let's review our summarization of the literature again. Left table shows that topological descriptors and their associated comparative measures have been used for a wide variety of visualization tasks. Right table shows that many comparative measures are available with nice mathematical properties. However, we observe that the measures appearing in both tables do not match very well. Many mathematically sound comparative measures have not found practical applications. On the other hand, some comparison-based visualization tasks have been developed using heuristics. The properties of the associated measures are not investigated comprehensively nor supported by theoretical guarantees. This indicates a gap between theory and practice. We now discuss some challenges and opportunities to fill such a gap. As shown in the table of mathematical properties, the computation of some metrics proposed for graph-based topological descriptors is NP-hard. This makes them feasible only for small graphs. Much more work is needed to develop algorithms applicable to large real-world data. One approach towards efficiency is to develop approximation algorithms for computing both topological descriptors and their comparative measures. For example, the Mapper graph is an approximation of the Reeb graph. We can approximate a Reeb graph with a Mapper graph while still preserving some topological structures. For example, the two loops shown in this picture. Both Table 1 and Table 2 show that few comparative measures have been developed for complex space topological descriptors such as Morse complexes and their variant. Computing these descriptors and designing effective comparative measures remain a challenge. In addition, defining features of interest in an application context is a challenging problem involving a variety of considerations. There have been some efforts to define topological descriptors that can be further augmented with more geometric or attribute-related information, such as the comparison of dual contour trees that establish correspondence based on node attributes. Heuristic strategies for node mapping can lead to the possibility of integrating domain knowledge into the comparison process. For example, in the case of extreme graphs. However, the heuristic strategies often lead to a violation of the metric and stability properties, and hence require a solid evaluation. We also see potential for the integration of topological methods into interactive tools and visualization pipelines for all visualization tasks discussed in this report. This integration will support the exploration and comparison of scalar fields and analysis of time-varying data and ensembles. The biggest hurdle to success in applications is the availability of the methods within open-source software such as ParaView and the Topology toolkit. Such tools allow visualization experts to integrate topological methods even if they are not expert developers of these techniques. To conclude, the development and deployment of visualization techniques and tools based on these comparative measures have impacted various application domains. We see current and future applications of comparative measures in structural biology, climate science, combustion studies, neuroscience, computational physics and chemistry and ecology. We want to thank all our collaborators and sponsors, as well as all the authors giving us the permission to reuse their images. Thank you for your attention.
Thank you for the very interesting survey and talk. We are ready to open the floor for questions. So please use the Discord channel and YouTube channel if you have a question. Okay, so I cannot see yet the question. I have one question. So are you aware, I saw on the slide 19 of the presentation, are you aware of a common model or framework that would encompass all topological descriptors? So you have this persistence diagram, the Reeb graph and its variants, the Morse-Mail complex, but they look like independent. Are they belonging to a common frame, or is there some work on this topic?
Okay, so most topological descriptors we described in our survey is rooted on the Morse theory. So they use different structures. For example, the contour-based, the graph-based topological descriptors such as merge trees, Reeb graphs are contour-based, and the complex-based topological descriptors such as Morse and Morse-Small complex are based on its gradient. So although they have different structure and appearance, they are rooted in the Morse theory. And if you have some mathematical problems, I suggest you to read our paper.
Okay, thank you. I see there is one question from Noeska Smith. So thank you for this comprehensive overview. I know very little of topological data analysis, but I've seen the Topology toolkit presented several times, which seems easy to use. You mentioned that practical applications are hindered when algorithms are not freely available. How can we encourage authors to contribute to these efforts?
I think most authors want more and more people to use their algorithms or newly proposed topological descriptors. So I will suggest the authors will have more communication with the domain scientists, and thus then they can have more user cases and show how their researchers and how their algorithms can be applied in the applications and some specific visualization tasks. So then, if the readers or audience think their applications or the research result is interesting, then I think more and more authors will contribute to the development of the software.
So I also like to add to this as well. So the few very useful ways to get topological tools to be used in visualization is to have open source implementations. In our survey, we have included a collection of open source implementational effort that is relevant to topological descriptors and their comparisons, but there should certainly be more of those. As the question also mentioned TTK, which I think is a very great effort in trying to unifying a lot of those open source implementation efforts specifically for topology and visualization. So to encourage authors to contribute more to this effort and to kind of encourage usage of those techniques, one suggestion would be try to integrate their effort through open source implementations, in particular like TTK, so that there is a, in some sense, a unified platform for especially topology in visualization. Of course, there's also ParaView and a few other platforms that is sort of like a community effort in this direction.
Okay, thank you. Are there already some tools which are integrated in TTK among the tools you mentioned in the survey?
Yes, in the survey, we provide a list of open source software, both for the to compute the topological descriptors and how to use the comparative measures between topological descriptors.
So
okay.
TTK already included things like persistent diagram, merge trees, contour trees, rib graph, and more small complexes. So and also persistent-based simplification. So a subset of the techniques that we discussed in the survey have already been part of TTK, but I would say there's still a lot of room and a lot of new techniques that could be integrated.
Okay. Maybe I have another question. All these techniques, so we are talking about scalar field, but between the topological tool and the scalar field, we need to have, I guess, a triangulation of some sort, right? To compute these topological indicators.
So the topological descriptors provide summarizations and capture the shape of the scalar field. So it is we have also plenty of topological descriptors that we can choose from. So this is a domain scientist problem. So we can identify which application tasks and which visualization tasks we want to achieve, and then we can choose which topological descriptors you want. And from the visualization tasks such as symmetry detections and clustering, we need comparative measures, and these comparative measures can identify the similarities between topological descriptors, and this result can then use to the visualization tasks. So, so I think we should have some pre-knowledge of the scalar field and then to choose which topological descriptors are used. Yeah.
Okay. Let me see if so. No question coming. I have another one. What are the limits in terms of dimension? For now, you study only two-dimensional scalar field, also three-dimensional scalar field. Are there limits? I guess there are, but for higher dimensional, or does it scale with the dimension of the field?
We not specify that we just use the topological descriptors in 2D scalar field. So I think so some works also use topological descriptors in high dimensional space. Of course, there are more and more new topological descriptors are coming and tackled with the high dimensional scalar field as well.
So most of the topological descriptors in terms of theory is not constrained to say has to be a 2D or 3-dimensional dimensions. For example, for things like persistent diagrams, your underlying point cloud could be sort of high dimensional point cloud. You can still compute persistent homology and persistent diagram or barcode. For example, for things like more small complexes, most of its application is for 2D and 3D domain. However, people could have approximations of more small complexes in high dimensional space. However, in that case that there's not sufficient sort of mathematical theory to talk about the quality of approximation in high dimensions. For things like contour trees, merge trees, rib graphs, again, the mathematical definitions is not constrained to low dimensional domain. However, in practice, especially in visualization, those graph-based or tree-based topological descriptors are typically used for sort of low dimensional domain 2D and 3D, but there has been cases where it could be applied to high dimensional domain. So in a way that, I would say all those topology descriptors we have discussed always have counterparts in sort of low dimensional versus high dimensional domain. It's more of, applications of them for visualization. A lot of applications are in 2D and 3D, but we have seen works also for high dimensional, say, parameter spaces where topological descriptors have to be useful. So in summary, those topology descriptors are not really constrained by the dimension of the of the domain. But on the other hand, there is certainly computational complexity when you increases when your domain becomes high dimensional, especially if you have to sort of compute pairwise distances or you have to kind of extract contours in high dimension. So
that means just to finish on that question. So the computing the descriptors in high dimension might be complex, computationally demanding, but what about the rest of the descriptor you mentioned? So the comparison between the field in your survey, you mentioned different aspects of this question. Maybe they are not impacted the same way. As soon as the descriptor are computed, it's easy to compute the rest, or maybe not. So how the dimension impact the other kind of part of your survey? Maybe my question is not clear.
So if I rephrase your question, are you saying that once I have extracted the topological descriptor from either low dimensional or high dimensional data, what is sort of, do I have any sort of complexity associated with its comparative measure that is dependent on the dimension of the input?
Exactly, yeah.
Is that the
or
question?
Is it everything is taken by the main, the first step, which is to extract this descriptor?
So, I mean, I can add something while Lin thought about from her perspective. For example, things like persistent diagrams. Once you have extracted persistent diagram from, say, a high dimensional, a filtration from a high dimensional point cloud, the comparative measure is just based on this diagram itself. That does not depend on the dimension of the point cloud where it's originally coming from. So that's one example. Think about topological descriptor as sort of the signature of your data. Once the signature extracted, then your computational complexity in comparing the signature is only dependent on the complexity of the signature itself, not the complexity of the sort of the original point cloud dimension. Of course, during the extraction process, most likely, getting this topological descriptor would be dependent on the complexity of your data. But once you have the signature, then it's very much dependent on the complexity of your signature or topological descriptor.
Yeah. So that's a kind of the bottleneck part.
Yeah, I think it's actually true, especially with respect to your persistence diagram or persistence barcode. But something different if we consider the more small complex and the merge trees. So merge trees can also be built in the high dimensional space. So maybe that will also increase the computational time.
So there's one thing I do want to add to this is that, if we have seen works in this domain where the comparative measure also integrate information from the original domain, like geometry information or domain knowledge. So in some sense that if you are coupling topological descriptor in the classic sense together with, say, geometry information from the data itself, then of course your comparative measure will be dependent on the complexity of the original domain. Depends on the type of information you are kind of coupling with the topological descriptors. So that will be, and we've seen some of those hybrid approaches in the literature as well. So in that particular case, the comparative measure using some domain knowledge or data information from original data would change its underlying sort of computational complexity.
Yeah, that's true. Such as more augmented contour tree and extrema graph, etc. Yeah.
Okay, thank you very much. And there is a last question from Fangfei Lan. In which application domains do you think topological descriptors are more popular? In which domains do you think topological descriptors could have more development in the near future?
Yeah, I think in my last few slides, I showed that the topological descriptor and their comparative measures can be used in many domains. So, such as in the biologies, we can use the symmetry detections to detect to highlight the repeating structures of the biomoxel in the biologies. And also we can use the topological descriptors to developing the cloud tracking method in climate science. And also we can study the combustion data set because using the pairwise comparison of topological structures, we can understand the different strategies of the combustion. So I think the topological descriptors is a very promising ways to understand the complicated real-world data set. And for the new topological descriptors, and just as Bei said, for the most of the classic topological descriptors, we do not include the geometric informations. But more recently, the researchers want to add more and more additional information from the original domain to enrich the information the topological descriptors carry. So maybe the new development of topological descriptors could be encode geometric informations, encode the pre-knowledge of the original data set to the topological descriptors, and then to provide more insights in the comparative process.
I also want to add two things. I think in the most recent research, there's at least two major fields that I see very increased activity in using topological methods. One is in material science and one is neuroscience. Those are the two, I think, fast growing areas that are utilizing topological descriptors for trying to summarizing the structure of underlying data. And if we're looking at application areas which will see more development, I think material science and neuroscience are definitely going to be very active over the next 3 to 5 years.
Okay, thank you very much. I don't see other questions, so maybe thank you again for the very nice presentation and for the questions. So I encourage you to continue the discussion on Discord and Topia, and let's thank again our speaker. Hello again. So let's continue this session with the next talk, which is visualization in astrophysics, developing new methods, discovering our universe, and educating the Earth. So the talk will be given by Fangfei Lan.
My name is Fangfei Lan, a PhD student from the Scientific Computing and Imaging Institute at the University of Utah. I will be presenting our STAR report, Visualization in Astrophysics, Developing New Methods, Discovering Our Universe, and Educating the Earth. This is joint work with my fellow graduate student, Michaël, astronomers Lauren Anderson and Juna Kollmeier, visualization experts, Anders Ynnerman, Alexander Bock, Angus Forbes, and Michaël Borkin, and my advisor, Wang. First of all, let me pose the question, why do we care about visualization in astrophysics? The answer lies in the path of astronomy. From an illustration of the Ptolemaic geocentric system by a Portuguese cosmographer and cartographer in the 16th century, to Galileo's sketch of Jupiter's moons in the 17th century, to nowadays a wavelength image of a molecular cloud, our observations and captures of the supermassive black hole, a reconstruction of the Milky Way, and a 3D printed model of a nebula. Astronomy has evolved dramatically. However, visualization has always played a crucial role in astronomical discoveries. Astrophysics is inherently visual, and modern astronomers are recording an increasing amount of information. These data present opportunities to make enormous strides in discovering more about our universe and state-of-the-art visualization methodologies. This survey aims to become a reference point for building connections and collaborations between two communities: data-rich but technique-hungry astronomers and data-hungry but technique-rich visualization experts. The STAR report serves as a starting point to bridge the knowledge gap between these communities. We want to help visualization experts better understand the needs and opportunities in astronomical visualization and provide a mechanism for astronomers to learn more about cutting-edge methods and research in visualization as applied to astronomy. We surveyed 80+ papers from the past decade in the fields of astronomy and visualization that contain strong visualization components for astronomical data, and classified them based on 3 dimensions of categories. In this talk, I will first introduce our primary, secondary, and tertiary categories, and discuss representative and unique examples based on the primary categories. Then I will present the challenges and opportunities in the field of astroviz that we identified through this process. Finally, I will introduce an additional navigation tool we developed to complement our categorization. Our classification of the surveyed papers is guided primarily by a set of data analysis tasks, secondarily by a set of visualization techniques, and finally by a set of topical areas in astronomy. We view these 3 categories as being on equal footing and not necessarily hierarchical. Instead, they're considered orthogonal dimensions and provide complementary viewpoints. We organize the literature according to these 3 categories to provide a means of navigation from task-driven, technique-driven, and topic-driven perspectives. We identify 5 primary categories of approaches based on data analysis tasks. They are data wrangling, which transforms astronomy data into formats that are appropriate for general-purpose visualization tools. Data exploration, where users explore a dataset in an unstructured way to discover patterns. Feature identification, which visually guides the identification and extraction of features of interest. object reconstruction, which provides an informative visual representation of an astronomical object, and education and outreach, where astronomical data and data products are made accessible to the general public. Our secondary categories are based on visualization techniques employed for astronomical data, and they include 2D and 3D plots, such as histograms, scatter plots, and pie charts, 2D images that use image processing techniques to generate discoveries of astronomy data, 3D rendering that creates a representation of 3D volumetric data, interactive visualization that includes techniques such as linked views, detail on demand, visual filtering, and querying, dimensionality reduction that transforms data from a high dimension into a low dimensional space, uncertainty visualization that communicates the uncertainties in astronomical data that arise due to the randomness in data acquisition and processing, and new display platforms such as data physicalization and virtual reality. Our tertiary categories are based upon a list of topics from the NSF Astronomy and Astrophysics Directorate. They are extragalactic, galactic, planetary, and solar astronomy. These categories are used as a cross-reference for an astrophysics audience. In addition, we labeled each paper with the tags simulated and observational astronomical data. We present the surveyed papers mainly based on our primary categories. Now let's dive into the first category, data wrangling. Data wrangling is the process of transforming raw data into forms that more effectively support downstream analysis. This process is an important step for astronomy visualization because raw simulation or observational data requires significant wrangling into a suitable form for visualization tasks. This table presents an overview of our categorization of data wrangling papers. We see that for our secondary category, data wrangling research emphasizes 3D rendering and interactive visualization techniques. Many of the papers placed in this category focus on transforming raw astrophysical data cubes into suitable data formats that can be ingested into open-source graphics and visualization tools, such as Blender and Houdini. Many of these techniques can be applied to multiple topical areas in astronomy, and both simulated and observational data. AstroBlend, introduced by Ynnerman, is an excellent example. The software extends the 3D graphics software Blender, making it possible to import and display various types of astronomical data interactively. It is an open-source Python library that uses YT, a software that analyzes and visualizes volumetric data to support the data loading and visualization process. Borkin et al. Presented a method for creating cinematic visualization and time-evolving representations of astronomy data. They introduced a detailed pipeline of importing nested, multi-resolution, adaptive mesh refinement data into the 3D procedural animation software, Houdini. Their goal was to create astronomy visualizations that are both educational and aesthetically pleasing. There are also efforts on advocating for certain file formats that are more suitable for visualization. Bolt et al. Proposed to improve the access and publication of astronomy data visualization using 3D diagrams based on the X3D file format, called X3D Pathways. They advocate for the X3D file format because it lies in the center of a variety of display formats such as movies and animations, 3D printing, interactive HTML, and PDF documents. X3D Pathway is file format dependent instead of software dependent, making it less likely to be affected by rapid technological evolution. Now let's take a look at our second category of data analysis tasks, data exploration. Data exploration facilitates the unstructured investigation of dataset in order to discover patterns of interest and formulate hypotheses. we present an overview of our categorization of data exploration papers in this table. Similar to data wrangling, data exploration tools span all 4 of astronomy topical areas and can be applied to both simulated and observational data. Most works in this section use 2D and 3D plotting to accompany the 3D rendering and interactive visualization in order to provide more statistical analysis functionalities. I would like to point out that we did not see any research work in the data exploration section with a component of uncertainty visualization. Although it is a bit surprising, this presents great research opportunities for the future. Some of the tools were developed with specific use cases in mind, such as ESA Sky. ESA Sky is a web application designed for the exploration of multi-wavelength skies and the visualization of the coverage of the ESA astronomy missions. The video shows the process of loading multiple skies and visualizing data of the ESA mission. There are also tools that support a large variety of tasks for astronomy datasets, such as OpenSpace and Gaia Sky. OpenSpace has already demonstrated its success at supporting educational and outreach activities in museums and in planetariums. It is also constantly evolving to facilitate scientific research. It exhibits a number of novel features, including globe browsing, which displays the planetary surface textures, and an atmospheric model that visualizes planetary surfaces. As new display platforms gain popularity, Vo et al. Presented N-Cube, a visualization software that can be used on a single desktop as well as in the Cave 2 immersive virtual reality display environment. A unique feature of N-Cube is its VR capabilities for comparative visualization. It exploits the Monash Cave 2's 4 rows by 20 columns configuration and displays on all 80 screens simultaneously. Each screen is selectable and interactive. Here's a number of selected screens from the visualization of different galaxy morphologies. Since its introduction, TopCat has been widely used to view, analyze, and edit tabular data in the astronomy community. Over the past decade, the developers of TopCat have continued to improve its capabilities, with a number of innovations in 2D and 3D plotting. One important new feature is a hybrid scatterplot/density map that enables users to navigate interactively between the high-density and low-density regions without changing plot types. For our 3rd and 4th categories, we have feature identification and object reconstruction. Feature generally means a measurable piece of data that can be used for analysis. We recognize that objects may be considered features with sharp or discontinuous contrasts in a dimension of scientific interest. Whether a specific aspect of a dataset is considered an object or feature depends on the scientific question posed. We separate these 2 categories to be compatible with literature, but we envision a future where these entities are recognized as a continuum. Now let's dive into the details of feature identification. The detection of features in an astrophysical data stream is important since many interesting phenomena are diffuse or observed with a low signal-to-noise ratio, and distinguishing between signal and noise is critical. In this overview table, we see a wider variety of visualization techniques used in papers of this category than in data wrangling and data exploration, including more examples of 2D images and dimensionality reduction. Although feature identification applies to both simulated and observational data, the majority of papers in this section focus on dark matter simulations and the cosmic web, which are extragalactic astronomical data. In particular, voids, filaments, and dark matter halos. Sheng et al. Built an interactive visual analysis system that focuses on exploring the evolutionary histories of halos. They proposed a unique particle trace path graph, which encodes the evolution history of selected particles, indicating the formation of a dark matter halo. Preston et al. Aimed to increase the efficiency and interactions in studying the evolution of halos described by merger trees. They used linked views to allow interactions between three views: the 3D rendering view, merger tree view, and quantitative analysis view. An important feature of the system is that it enables simultaneous exploration of heterogeneous cosmology data. Felix uses a topology-based framework to identify cosmological features. It focuses on extracting the filamentary structures in a dark matter simulation. The filaments are displayed in the orange tubes, and the three figures are generated from adjusting the query parameters. It incorporates a visual exploration component by allowing the users to interactively query for specific density ranges. Tampaka et al. Applied deep learning to estimate galaxy cluster masses from Chandramak, which are simulated low-resolution X-ray images. They used a relatively simple convolutional neural network, but their main innovation is the visual interpretation of the CNN, using an approach inspired by Google's Deep Dream. Comparing the left and right image, we see that in the right image, the CNN misclassifies the cluster core above and to the right of the true cluster core, which lies in the center of the image. Their work illustrates the utility of interpreting machine learning black boxes with visualization, since it provides physical reasoning to predicted features. We now move on to the object reconstruction category. Object reconstruction provides informative visual representation of astronomical objects. From this overview table, we see that research works in this section have a strong emphasis on observational data and the use of 3D rendering as the main visualization technique. I do want to point out that there are two works in this category that build uncertainty visualization into their reconstruction pipeline. This is often considered difficult for astronomical data. We'll discuss more about it in the challenges section. Now let us look at some examples in the object reconstruction category. Using the positions and distances of thousands of classical Cepheid variable stars obtained through observations and accounting of the stars' pulsating periods, Scorin et al. Constructed a 3D map of the Milky Way galaxy. They used 2,341 such stars to sketch the Milky Way galaxy and observed the warped shape of the galactic disk. Polyform is an interactive visualization and filament reconstruction tool that enables the investigation of cosmological datasets. In contrast to filament extraction tools such as Felix, Polyform is able to reconstruct the cosmic web from galaxy observations. Its fast computational simulation method is inspired by the foraging behavior of a type of slime mold. Simulation data often possess inherent uncertainty because of manual errors and measurement inaccuracies. Bock et al. Proposed a multi-view visualization system that uses uncertainty visualization to verify simulation results of the Sun's corona mass ejections. The left figure shows the ensemble view of a number of simulations and its associated uncertainties. The system also integrated a 3D spatial view of the simulations shown in the right image. Finally, we introduce our last category, education and outreach. In an ongoing paradigm shift in scientific outreach, technological advances are enabling data-driven and interactive exploration to be possible in public environments such as museums and science centers, increasing their availability to the general public. Here we present the overview table. We see an overwhelming popularity of 3D rendering and interactive visualization techniques used in this section's works. These techniques are often used to create large-scale immersive environments for planetarium dome theaters. More recently, there has been a greater focus on interactive methods where the user becomes part of the exploration. New display platforms, such as augmented reality, virtual reality, and 3D printing, are emerging and exciting mechanisms for science communication and broad dissemination. Here I present an example of an interactive presentation in a large-scale immersive environment to the general public. It is an image taken at the Brilliant Minds conference. Software such as OpenSpace and Worldwide Telescope are among the most popular tools that are used to create scientifically informative and aesthetically pleasing visualizations for these immersive environments. Worldwide Telescope is a virtual observatory for the public to share and view data from major observatories and telescopes. The open source software provides the capability to visualize the solar system and stars and show observational material in context. Virtual reality and augmented reality are also used in museums and science centers. Arkin et al. Developed a 3D VR and AR program to visualize the Cassiopeia A supernova remnant, giving users the experience of walking inside the remains of a stellar explosion. Madhur presented a case study using 3D printing to visualize the Eta Carina Homunculus Nebula. The 3D models not only facilitate research discoveries, but also help communicate scientific discoveries to non-astronomers, especially to the visually impaired. In addition to a taxonomy of existing approaches that utilize visualization to study astronomical data, our contribution includes a summary of the current challenges and opportunities in visualization for astronomy. The major challenges are data volume and diversity, interactive visualization and intelligent querying, uncertainty visualization, time series data visualization and analysis, machine learning, and further advancement in education and outreach. We review 3 of the representative ones here. As we've seen from this presentation, uncertainty visualization in astronomy remains largely unexplored. We present here the 2 examples we found from the object reconstruction section. Errors and uncertainties are often introduced due to data acquisition, transformation, and visualization. But applying uncertainty visualization to 3D astronomy data is challenging because we lack the techniques to deal with sparse and faraway samples and their large error cones. However, the potential exists to display uncertainty in a localized object or regions of interest, and that potential must be developed further. Most of the current time series data visualizations are built to display halo evolution as we presented here. The technique often used is the merger tree visualization. In general, time series data visualization can also be helpful when tracking star movements. However, little effort has been expended in this regard, with Gaia Sky being the only example, to the best of our knowledge. Time-dependent visualization, in particular, the interplay between spatial and temporal dimensions, will be crucial as more time series astronomy data become available in the near future. Many astronomers voice their desires as well as concerns about using machine learning techniques, and in particular, deep learning, in the astrophysics discovery process, mostly surrounding the interpretability of black box ML models. Most works we've seen so far have used convolutional neural networks for classification tasks. We believe that combining visualization with machine learning models has the potential to make the results more accessible than classical interpretations. A good starting point to obtain interpretability is to combine visualization with models that are inherently interpretable in studying astronomical data, such as linear regression, decision tree, and naive Bayes. Topological data analysis that promotes topology based on supervised learning techniques also has great potential in its application to scientific visualization. Together with the classification and descriptions of papers, we provide a navigation tool where the surveyed papers are distributed along 2 axes. This tool provides a different viewpoint for the state-of-the-art survey. The first x-axis, single task versus general purpose, specifies whether a specific paper addresses a singular challenge of visualization in astronomy, or whether it describes a more general-purpose system that can be applied to a wide array of potential applications. The second y-axis, technique versus application, specifies whether a paper develops a specific visualization or analysis technique, or whether it combines many different techniques to address a specific application. Let's try to embed some of the examples we went through today into this plot. Let's start from the top left quadrant, single task and application. We have the 3D printing of nebulae and the VR system of a star remnant. For the application and general purpose quadrant, we have software such as AstroBlend, Worldwide Telescope, and TopCat. For the general purpose and technique quadrant, we have the X3D pathway example. And for the single task and technique quadrant, we have the cinematic visualization system and the filament reconstruction system, Polyform. Here we have the complete navigation tool. The primary category, data analysis tasks, is double encoded with colors and marker shapes. We lay out the papers in their general areas in the figure to avoid overlap of labels. On the opposite diagonals of the single task and application quadrant and the general purpose and technique quadrant, we see fewer papers, indicating research opportunities in the near future. To make the survey results more accessible and actionable to the research community, all papers surveyed, including associated metadata, can be explored online with a visual literature browser developed with the Surveys framework. We embedded an interactive version of the navigation tool here as well. A major finding of this work is that there remains a significant gap between cutting-edge visualization techniques and astrophysical datasets. We therefore take this opportunity to issue a call to action for both the visualization and astrophysics communities to consider more robust and intentional ways of bridging the gap between visualization methods and astronomy data. We make the specific recommendations below as concrete suggestions for improving this goal over the next decade. We suggest the construction of a comprehensive AstroVis roadmap for bringing these disparate communities and stakeholders together at both the grassroots and institutional levels. In order to build community, we suggest regular annual joint meetings that will explicitly target this gap and bring together visualization and astrophysics domain expertise. To assist in the access to information and literature, we suggest that an AstroVis keyword be added to papers published in either astrophysics journals or visualization publications to make interrogation of papers easy for the communities. We further suggest starting visualization and data challenges within the large publicly available astrophysics data surveys. We are encouraged by the progress that has been made in the last decade, and we look forward to the next decade of development, discovery, and education. Thank you.
Thank you for the very interesting talk. We're ready to open the floor for questions. So I see a question by Noeska Smith. So this is of a tangential question, so feel free to save it for last if there are more questions. Yes, sorry for reading that. I noticed a lot of similarities in the challenges that also occur in medical imaging data visualization. Are there bridges which we can make, or are such application domains too fundamentally different?
So I've actually thought about it a little bit. When I was attending this past year, I went to the uncertainty visualization session, and then there was this really cool research work that was done for medical imaging that they did uncertainty for 3D imaging, which is actually very difficult in general, I think. And I was thinking at the time, because I was working on this paper, and I was like, can we somehow translate this technique into 3D astronomical data, because astronomical data currently doesn't have a lot of uncertainty visualization techniques applied to it, because it's like considered very difficult. But then I think because of this, I think that there's actually lots of things that we can do to bridge, to like transfer the techniques from medical imaging into astronomy. Maybe we don't have too much communication between experts right now, but I think if we really need to encourage like this type of communication between disciplines. And I think one way that this survey is really trying to do is to open up this door to experts in all of the different disciplines. And I think one way that we're trying to achieve this is by classifying the works, not through just astronomy or visualization terminologies. Instead, we're classifying the works based on very generalized data analysis techniques. I feel like if we do this more in other fields as well, then it would attract a little bit more attention, because people can go in the survey or go in a research work and think that, okay, maybe I'm dealing with this type of data visualization or data analysis task as well, even if it's in a specific scientific domain. So I think that would be a really good way to encourage communications. So to answer your question, I don't think they're too fundamentally different. I think there are many techniques that can be transferred, and I really think people should think more about it.
So I think this is a really amazing question too, because I think if we are thinking philosophically, if the universe is a human body, then the stars are its organs. In some words, we're still talking about feature extraction, object reconstruction, and so on and so forth. And I think a lot of techniques developed across those two different subdomains of visualization could be transferable. So I think that's a really excellent point. And thank you.
Okay, thank you. There is another question from Noiska Smith. So more general question about surveys in general. If there are few papers in certain area, does that automatically mean it needs to be explored, or that mean maybe there are reasons for these gaps that exist? So it may be a not useful direction for research. What do you think about what you observe in your survey?
I definitely don't think it's less useful. I just think that maybe it's more difficult, that we currently lack the technique to explore more. And then I think a lot of, like, we've had a lot of conversation with astronomers, and they've voiced a lot of, just they don't have, I think the current communications between different disciplines are still very lacking, and that's a major reason why I think astronomers sometimes, even if they want to do something, they don't have easy access for the resources to do it. So I do believe that there is a lot more space to be explored, especially in these regions where we have fewer research. And I think like we have to explore it first before we can say it's useful or not. And currently we just don't have those when there is a gap.
Okay. So maybe another question by Vijay Natarajan. Are visualizations integrated into public astronomy data repositories? This appears to be very common in the field of biology and has helped the field.
So visualizations integrated into a public astronomy data repository. So if you're looking for, I think there are lots of public visualization for astronomical data. I don't know if they're necessarily integrated into the astronomy data repositories, but if you're looking for very good public education or visualization examples, there are many of those, and then most of these visualization softwares are actually open source. So for example, like OpenSpace, you can just download it on your computer and then play with whatever that's inside, and then play with, and then load the data into open space, or many other software such as like YT. Also, you can do some simple analysis by yourself if you would like to. And I think one thing that I would like to mention is the glue visualization environment. That is a very cool open source environment. And that one hosts a lot of astronomy data inside of the environment. And it also gathers a lot of the open source astronomy visualization and analytics tools in the same place. So you don't have to go to different places and look for different tools. So you can actually go to that one place and have many astronomy data and also the tools that can be used to analyze and visualize the data. So it's called the glue visualization environment. So that
sorry, go ahead.
And that is integrated into the public side of things.
Yeah, I also want to add, for example, for public astronomy data repositories such as SDSS, there also have been tools that is part of SDSS, for example, things like Sky Server and so on, which actually provide some visualization capabilities as part of SDSS Sky Survey. So it has ways to visualize and explore astronomy data in regions of the sky covered by the Sloan Sky Survey. So yes, there are also a bunch of sort of visualization capabilities that is bundled together with astronomy data set.
Okay, thank you. I have a question. So these data are inherently 3D and plus extra information. So they are multidimensional data, but they have a 3D component. So do users also use virtual reality to explore this data? What is the pros and cons in each in astrophysics?
So you mean how do users explore 3D data? Is that your?
Yeah, do they use virtual reality environment, or they use always 2D screen? And
yeah, so there are
what is the most common?
Yeah, so I think up until recently, most of the exploration are done on a 2D screen, which you can imagine it could be sometimes difficult because we're envisioning a 3D space on a 2D screen. But then there have been recent developments in virtual reality, especially, I mean, if we talk about research software, we now have OpenSpace, which can be used as virtual reality. And then there are also other virtual reality displays in museums or like science centers where the users can put on a headset and then go in to a space and walk through like a supernova remnant or something like that. And then if we talk about more broad dissemination of virtual reality applications, we also have plenty of those where the users can kind of go in and play sort of like an astronomical educational game. There has been a lot of development on that as well. And then, but then I do think with the 2D, on a 2D screen, a lot of the applications are still very useful, especially for, if you don't have a VR headset. I think there's still a lot you can do on a 2D screen. Yeah.
What about in that case about the scale? Because in astronomy, you have this very, very vast difference between scales. I guess a galaxy, the universe, planets are very, very different scales. And so is there some work comparing the perception of scale in 3D and in 2D for this specific kind of data? Are you aware of this sort of work?
I don't know if they would compare them, but there are definitely lots of techniques that deal with this, because you are right that the scale is difficult to develop techniques for. Especially, I think this is like the most important reason why we don't have a lot of uncertainty visualization in astronomy, because you can imagine the error cones could be very large for far away samples, but would be smaller on local samples. So I think that's one of the most important reasons. I don't know if they actually compare the scales, but they do develop techniques to navigate from like a localized region to a faraway region. So there's lots of techniques when it comes to, let's say, if I'm doing like a space exploration, then I have to think about how I would travel in space from a localized galaxy to some faraway astronomy object.
Okay.
So yeah, I would like to add a little bit. I think in our survey, we actually specifically pointed out the astronomical data. One of those main challenge is both its volume as well as its diversity. One of the issue is that with the increased large data set for astronomy data, it actually become an immediate challenge to try to apply many of those interactive capabilities that oftentimes visualization experts would love to have. That is one. The second one is actually there is a lot of heterogeneous data sets out there for astronomy, and then how to actually connect and relate those heterogeneous or diverse data set in astronomy is actually a really a big challenge, in addition to just simply the volume of the data. And there has been sort of a growing open source community and collaborative environment, as what Fei mentioned. For example, like GLUE, one of its effort is actually try to integrate very diverse and heterogeneous data sources for astronomy. So those both volume and diversity is actually the challenge for astronomy data.
Okay, thank you. And so I don't see other question. I have a last one. What are the trendy area in this field? Can you elaborate on the most interesting maybe opportunities you see in this area?
So I think we definitely mentioned a lot of this in the challenges section in our paper. If you're more interested in details, you can go read it. But yes, so I think time series analysis is one of the most important ones right now, because I think we're now starting to record more and more time series data. This interplay between the temporal and the spatial dimension really needs to be explored more, because I think now a lot of the time series visualization are around like halo evolution, but then there's actually a lot more you can do, such as like how do we visualize star movements? And that is definitely a time series data, but right now we don't have much about it. And then, so apart from that, I think uncertainty visualization needs a lot more new development, not necessarily like, because I don't think there's much development for uncertainty visualization in astronomy right now, but I do believe there can be a lot more if visualization experts and astronomers communicate a little bit more. I think there should be a lot more development in that field. And then machine learning currently has some applications in astronomy, but I think most of it is kind of contained in this like convolutional neural network type of works. Most of it is actually based on convolutional neural networks, because astronomy has a lot of image data. And I think there's a lot more. And then I think astronomers are concerned because they feel like machine learning techniques are black box techniques, that we don't understand a lot of what's going on, and it's very important to understand the physical meanings of the results in astronomy. So I think that's why a lot of astronomers kind of turn away from these techniques. But I do think we're having a lot more efforts nowadays to interpret the machine learning models. And I think visualization is such a good way to interpret machine learning models. And so with visualization and machine learning, I think there could be a lot more development in astronomy, astronomy and data analysis. And then also Bei and I do a lot more of research in topology, so I think maybe we're a little bit biased in this, but we do think astronomy data is very geometrical and topological, and we do see a lot more application. Like we really want to explore more in this domain, because right now I think a lot of the topological data analysis applications in astronomy are just based on discrete Morse theory. Like that's kind of the only thing. Or like there's one paper on the Poincare map but that was about it. Like there's not much done in this field right now, but I think there can be so much more. And then I think we did mention a lot more on further advancements in education and outreach also. I think nowadays people have a lot more access to screens, right? Like we have our tablets, our phones, our laptops, and then we can go to the museums easily. I think there should be a lot more effort into this education and outreach section where we, you know, like develop more effective interactive visualizations for astronomical data to communicate to the public that, you know, we live in the universe, but we know so little about it, especially the general public. Like, honestly, I knew very little about astronomy and like specific questions in astronomy until I read so many papers about it. And it's so interesting. I just feel like so many people could be more interested in the field if we actually tried harder to communicate this with the general public. Yeah, Fei, do you have anything to add?
Yeah, I mean, I just want to emphasize the last bit where I think there's a lot of excitement. You know, open space is a really good example of the usage of AstroVis in science communication. I think there's a lot of excitement happening in that space, and we hope to see a lot more development for science communication in astronomy. So,
okay. Thank you very much. I don't see new questions, so I guess it's time to wrap up the session. I would like to thank again all the speakers. Thank you, the audience, for your questions, and also thank the volunteers and technicians for handling the session and questions. Hope you enjoy the rest of the conference and see you soon.
Thank you very much.
Thank you.